Well, tonight I won't make much noise. I'll hand over to our speaker tonight, Dr. Robin Wilson.
Thank you very much. Good evening, everybody. Thank you all for coming. As you said, my name is Robin Wilson. I did my PhD at Southampton University here, and my undergrad as well, in fact. And I now work as a freelancer, working on some of the sort of stuff that I'm going to tell you about today. So can everyone see okay? You're not looking through me to see that? No? Okay, cool. Right, so monitoring the environment from space. Let's start off with a picture that is not taken from space, as you can probably gather. This was a picture of Kenilworth Castle in Warwickshire, taken on one of my holidays one year. And I want to ask what seems like a silly question, which is, how do you know that that bit of the picture is sky, that bit is the castle, that bit's trees, and so on? What do you use in the image to work that out? Someone shout out an answer.
Colour.
Colour, okay, great. So colour is one of the primary things you can use, but if it was a black and white picture, you'd still be able to work out what was what.
Shape.
Shape?
Lines.
Lines, sharp lines.
Position.
Sorry? Position, yeah, context. You know, sky is kind of at the top, grass is kind of at the bottom, that sort of stuff, yeah? Reflection, things like that, great. So we're going to come back to all of those things throughout the talk and use the same sort of methods that you use when looking at a picture like that and interpreting it to interpret satellite images. But first of all, we're going to think about the trees in that image and say, okay, the trees there and the grass there, they're both green. But why are they green? Well, they're green because when light shines from the sun onto the tree, and light shines in a lot of different colours, here we're representing it as red, green and blue, which we'll come back to later on, but light comes from the sun. What happens is that some of the red light and some of the blue light gets absorbed by the tree, but the green light gets reflected very strongly, and so it gets reflected into our eyes, and that's why the tree looks green. So we can look at this image in a bit more detail if we split the image up into its component parts. Now this image was taken with a digital camera, and digital cameras record the amount of light coming in the red, the green and the blue parts of the spectrum separately. And these are the separate bits of the image. So you've got blue, green and red. Now, if you look at these, they're slightly strange to interpret, these single colour images. Basically, the whiter a bit of the image is, the more of that colour there is. So you can see here the sky is almost entirely white in the blue image. That's because there's lots of blue in the sky. But you see that there's not much blue in the grass down here. On the green you can see it's lighter coloured on the grass, so that's a high amount of green there. Red, the castle itself is coming up quite white, which means there's quite a lot of red in the castle. So those are the kind of components of the image. Something again that we're going to come back to with satellite images in a moment. And one final bit about things that make up an image. You've probably all heard about pixels. Things like digital cameras are measured in megapixels, which is the number of individual dots in the image that they record. So if you zoom in on an image, you can see it's made up of lots of little squares, and all of these squares have a value. They have a number in that, which is representing the intensity of light in that little area for that particular colour. Now, as I'm a scientist, when I get numbers like that, I want to plot them on a graph often. So you can produce a graph that's a bit like this. So this is a graph of four different things that you find in the image: sky, grass, castle and tree. And what we're doing at the bottom here, we've got blue, green and red, and we're just plotting the numbers that are recorded on the digital camera for each of these colours. So you can see the sky has lots of blue, some green and not much red. The castle is kind of opposite, not much blue but lots of red. The grass and the tree both have a kind of peak in the green because they look green, that's as you'd expect, and they're kind of lower down for the blue and the red there. Now, this is a nice useful graph, but we can make it a bit better by putting numbers on the colours and converting the colours to their wavelengths. As a number of you will probably know, light is part of the electromagnetic spectrum, which stretches right the way from gamma rays and X-rays right through to radio waves. But the only bit we can actually see with our eyes is this visible light in the middle, which stretches from the blue part of the spectrum at about 400 nanometers, up through green and red, to the red part up to about 750 nanometers. So we can do exactly what we did with the graph just now, but just put numbers on the bottom instead. So this is wavelength in nanometers now. I'll be showing a number of graphs that look a bit like this, with wavelength on the bottom and the intensity of light up on the left-hand side there. And so it's exactly the same kind of graph, it's just squished a little bit. And these graph patterns are what we call spectral signatures. So this is this kind of signature of a particular thing in the image. It always, all the sky will have a particular sort of pattern on this graph. All the graphs will have a particular sort of pattern on the graph. We're going to come back to those spectral signatures in satellite images in just a moment, but before we go on to that, I thought I ought to show you a few pictures of satellites and satellite images. So this is a animation of just some of the Earth observation satellites that are orbiting Earth at the moment. These are some of the ones run by NASA. There are hundreds of satellites in Earth orbit. A number of them are for things like military purposes or for doing things like satellite TV and communications. But a number of them look down at the Earth, taking pictures of the Earth. And most of the ones that take pictures of the Earth, at least the ones we'll be dealing with today, work on a polar orbit. So you can see the orbits always go round, going over the two poles and going round, and the Earth is turning underneath them. So as your satellite basically sort of stays in one place going round and round, the Earth is turning underneath it, so the satellite over time gets to see the whole of the Earth as the Earth passes underneath it. Now we've had Earth observation satellites up in space for quite a long time. The longest running series of satellites is called Landsat, and it's been running since the early 1970s. 1972 was the first Landsat satellite, and they've all been designed to be broadly compatible with each other, so you should be able to look back with broadly similar imagery back to the 1970s, and the most recent one was Landsat 8, which was launched in 2013. I remember going to the launch party at the university where we watched the launch, and Landsat 9 should be launched possibly in 2020. I don't really believe that. I think it's more likely to be 2021. But the idea is they all overlap with each other, so you don't end up with any times where you haven't got any coverage. This is what the Landsat 8 satellite looks like. It's got a big solar panel to power it. It's got a load of things in the body of the satellite here, computers, power units, and thrusters to move it around a bit so it can change orbit and avoid other things in space if it needs to. But then the key bit is down here. This is basically a telescope pointing at Earth. So it's zooming in, magnifying what you can see on Earth from space. And then it's got a camera at the back that's very much like your digital camera or the camera in your phone. It uses the same sort of technology, CCDs, and records images just like the images that we were looking at earlier of the castle. Except these images, in my view at least, look a little bit prettier. So this is a Landsat image of Southampton. You can see Southampton Water down here, Southampton City itself, going up to the airport and Eastleigh, and then up eventually to Winchester at the top there. And Landsat has a resolution, a spatial resolution, we call it, of 30 metres. That means that every pixel in the image, so each one of these little dots, these little squares that the image is made up of, covers an area of 30 by 30 metres on the ground. And it's kind of an average, really, of what you can see in that kind of area. It's also got a temporal resolution, or a revisit time, of 2 weeks. That means you get a new image of the same place on Earth every 2 weeks. It basically goes, the Earth turns round and round and round, and it kind of does bits here, bits there, and then it fills in the gaps gradually, and over a 2 week period it goes back to where it started from, so you can get the same image again. If you zoom in a bit more, you can start to see the pixels themselves. So does anyone recognise where this is a satellite image of? It's somewhere local. Sorry?
Tottenham.
No, not Tottenham. Good idea.
Aldbrook.
Sorry?
Is it Aldbrook?
No.
Is it north-south for a start?
It's north of us here.
No, I mean the...
Oh, sorry, yes, it's north upwards. Yes, it's north upwards.
The university.
No, this is actually Winchester. This is the M3 running up here. These are the industrial estates where B&Q is and so on up at the Winnell roundabout. You've got Winchester itself here. You can actually see this little red bit here is the running track at the Winchester Leisure Centre that's just on the, when you come in the Bar End Road, the leisure centre there. So you can see quite a lot of detail. This is a series of images from Sentinel-2. So Sentinel-2 is a newer satellite run by the European Space Agency, and it produces data at a bit higher resolutions. This is 10 metres, so every 10 by 10 metres on the ground. And you can get, because they've got two satellites that are spaced apart from each other in orbit and kind of go around like that, you actually get data every 5 days. And this is part of Southampton Docks, so this is kind of Millbrook here. It's a bit difficult to see, but this is the Totton flyover across the river there to Totton over here. And you can see, over the time, different things changing. So you've got ships coming and going from the docks here. You can see the changes in the farmers' fields down here. You can even see changes in sea level. So occasionally, one or two of the images, you can see a sort of sandbank or the sort of bit of the coast, kind of over here, which kind of comes and goes depending on what the tide was like when the image was taken. You can also get images with far more detail. So this is an Iconos image. Can anyone tell me where this is? This is a bit easier.
Eastleigh?
Yep, this is Eastleigh. This is Southampton Airport here. This is Eastleigh, Chandler's Ford over here, the M3 going up there, and this is the Eastleigh Railway Works and all the other industrial bits around here, and the railway line going off towards Fareham and down to just outside here, of course. So this is 4 metre resolution. Now this isn't the highest resolution you can get. You can actually get commercial satellite imagery now that is about half a metre resolution. So every half a metre on the ground you can see in a pixel on the image, which means basically if you lay down it can almost see you because you're almost half a metre kind of wide and you're more than half a metre long. In fact, the really high resolution stuff is concerned about what uses it should be put to and ethical implications about that. But if you zoom in on this image, this 4 metre image, you can start to see quite a lot of detail. So you can see, if I move out of the way slightly, you can see cars and lorries on the M27 down here. You can see cars in the car park, markings on the runway. You're really quite a lot of detail. You can also go to the other extreme and go to lower resolution data, which is actually quite useful when you're looking at broad areas. If you try to look at the whole world at 4 metres, you'd have a huge amount of data. So it's a bit easier to look at it at a slightly lower resolution. So this is modest data, which is 1 kilometre resolution. You have a trade-off always between the spatial resolution and the revisit time. The lower resolution it is, the faster you can get a new image. So this one you get images twice daily, but it's only 1 kilometre resolution. And you can see just about, if you ignore all the cloud, which is why I'm showing this image, because cloud is a big problem for satellite imagery because you can't normally see through it. But if you ignore the cloud, the Isle of Wight is about here, Southampton is just around here, and this bit you can see just down here is the Isle of Portland, I think. So, what can you do with these satellite images when you've got these pictures? Well, the first thing you can do is just look at them and see what you can see. And this has been done for years. This is an example of an aerial photo that was taken in World War II. Reconnaissance photos. The area circled is the location of Colditz Castle, which was a prisoner of war camp in Germany. This was taken by the Allies before the sort of liberation of the camp. So, same kind of things can be done from satellite imagery. For example, these sort of images. These were taken by a satellite over a village in Nigeria a few years ago now. I think it was 2015. In the top image, you can see lots of trees. Whoops. So, yeah, lots of trees that are. There we are. It's better. Yeah. There we go. Perfect. You can see lots of trees which are in red. I'll tell you later on why the trees are in red. And you can see all sorts of buildings in amongst the trees. In this image, there's not many trees anymore, and all the buildings have been razed to the ground. So this was after a Boko Haram terrorist attack on this village. And you can monitor these sort of things from satellite when you've got high enough resolution data. And that obviously saves putting people into the field to try and work out what's going on in potentially very dangerous situations. Another thing that's quite useful is to do this after disasters. So this is the centre of Kathmandu after the 2015 Nepal earthquake. So the left-hand one is before the earthquake. You've got a nice park, you've got lots of buildings. After the earthquake, you can see loads of tents and loads of temporary buildings in the park for people who've been displaced from their normal homes. And you can see damage to some of the buildings around the side there. So again, you can make assessments of the damage and impact of an earthquake without trying to send people out into the field. So, we talked before with the digital camera about how we recorded data in blue, green and red. And we call those bands, wave bands or bands. And actually, the visible light is only a small portion of what satellite sensors like Landsat measure. So this is the visible light here in red, and Landsat's got 4 bands in the visible light, 2 that are around the blue, a green one and a red one. But then importantly, they've got 3 more bands in the infrared. So this is light we can't see, but that can tell us some quite interesting things, as we'll see a bit later on. So we've got one in the near infrared, so near infrared there, and two in what we call the shortwave infrared. So, just like we had a graph like this before for the different parts of the castle photograph, we can do exactly the same thing with spectral signatures looking at different parts of a landscape image. But we've got extra bands, so we've got a wider graph with more information on it. So this, for example, is the spectral signature of forests in a landscape image. So what we can see here, this is low wavelengths here and high wavelengths here, so we've got the visible light is these first four dots here, and then we've got near infrared and shortwave infrared. So we see that forest is low in the blue, that makes sense, forest doesn't look very blue, fairly high in the red, green, fairly high in the green because forest looks green, low in the red, and then the interesting thing is it's really high in the near infrared. That's something we can't see with our eyes, but the satellite can see that for us, and then it kind of drops off. If we look at a green field, we see that we get a very similar pattern. High in the green, low in the others, high in the near infrared, but the whole thing's kind of shifted up a bit because green is a bit brighter overall. Farmers' fields, green fields are a bit brighter overall than forests are. If we add urban areas into the graph, you see we get a very different sort of shape to the graph, so a sort of gradual increase and a sort of flattening off. And then water is completely different. Water, we can see high blue values, moderately high green values, and then everything else is so low it's basically zero. And there's almost no reflectance at all for water in the near infrared or the shortwave infrared. All infrared light is basically absorbed by water.
So would that therefore be invisible? Effectively invisible?
In the near infrared band, it would show up as basically zero. So it would look like, yes, it would show up the same thing as if it wasn't seeing any light, basically, yes. Yeah. So these again are the spectral signatures that I've been talking about before. And the amazing thing we can do then is we can look at each pixel in an image and say, okay, which of these graphs, which of these lines on the graph does it look most similar to? Does it look most similar to the forest or most similar to the urban? When we work out which one it's most similar to, we say, all right, well, we'll count this pixel as urban or forest. And rather than us doing it manually, going through thousands or millions of pixels in an image, we do it with computers. And the way that computers do it, basically, is by plotting a graph like this. Here we've got the blue, the brightness in the blue on the bottom, and the brightness in the red on the left here. And you can see the different colours here are different sorts of land cover. So you've got red here is different sorts of urban area, you've got pasture and hay up there, you've got shrubland up here, and they're all sitting in roughly the same place on this graph if they're a particular sort of land cover. So what we basically do is we teach the computer to draw lines around the different groups in a form of machine, a very simple form of machine learning, sort of artificial intelligence, but very simplistic. And then when we get a new point that goes here, for instance, we know, oh well, it's likely to be the same land cover as the rest of the group that's sitting that kind of place on the graph. And so this is the kind of output you get. This is the Korean land cover map, which is produced by the EU across the whole of Europe. We can zoom in a bit to the local area, and you can see we're noticing all sorts of different land covers here, not just the four that I mentioned earlier. We've got urban areas in red with a different sort of urban area, I can't remember exactly which type it is, in purple there. We've also got the sea here. You can see these purpley bits down here are intertidal zones, and you can see in the New Forest that we've got various different colours for different sorts of land cover in the forest. So the kind of heathland, the forest, the grasslands and so on that you find in the New Forest. The amazing thing is you can also do this for the whole world, because we kind of know what the land cover is in the New Forest and Southampton. We've got things like OS maps and stuff. But we don't necessarily know what the land cover is like in the middle of the desert or the middle of the rainforest. So we can do this for the whole world. This is Glob Cover, which is a global land cover map produced almost a decade ago now, but similar maps are being produced still. And that's how you get these estimates of how much land in the whole world is covered by desert or forest, from these sort of maps. The other thing is, I mentioned earlier, of course, that satellites take repeat imagery every few weeks, every few months, whatever. If you look at even just imagery every year and compare it over time, you can start to work out how your land cover is changing. Is your city growing and taking in the suburbs and the countryside around it? Or, particularly interesting from an environmental change, is your forest being cut down. So this is the Amazon rainforest, green is forest, red is area that has been lost through deforestation in the last, I think this was 10 years. And actually, if you do a few slightly different methods, you can look at the amount of forest loss in each area. So this scale of red from sort of black to red shows how much forest loss there's been. So let's just go back and have a think about these bands for the moment. We'll actually have a look at each individual band by itself in the same way that we did with the castle at the beginning. So we're going to use this image. This is, we've got Eastleigh here. This is the top of Eastleigh, Chandler's Ford here, the M3 going up here, and Winchester here, and lots of farmers' fields and things all around the place. So if we look in the blue band, and I'll just put a little copy of the colour image at the top there just to remind you what you're seeing, you can see you get quite high blue values, this white sort of colour, showing high blue values for the farmer fields. So they're reasonably, they've got a reasonable amount of blue coming to be shown. Lots of green. If I switch between the two, you can see you've got a lot more green on the farmers' fields, but really not in these urban areas. If I switch to red and kind of go again, switch back a bit, you see, well, there's less red in the farmers' fields, but there's more red, a bit more red in some of the buildings in the urban area. And then this is the one that's particularly different. If we just switch between the red and the near infrared, which is this one, so you've got red to near infrared. If you look at a particular field, so focus on that field, for instance, you see it's low in the red, but really high in the near infrared. And something that's high in the red here is really low in the near infrared. And that's because all plants, as we saw on the spectral signatures graph earlier, all live growing plants reflect really highly in the near infrared. And that's something really powerful that we can use for a lot of analyses. So, first of all, let's have a quick look at a true colour composite. So this is what I've shown you so far. This is the kind of picture you would see if you were sitting on top of the satellite and looking down, or looking through the telescope and looking down. It's just a natural photo like you take with your camera. And this is, as you can guess, the Isle of Wight. This is Hurst Castle here, and you can see things like individual boats in the Solent and their wakes and so on. So what we're doing here is we've got three colours we can display on a computer screen, red, green and blue, when everything else is made up of a mixture of those. And we're just displaying the red as red, the green as green, and the blue as blue. Makes perfect sense. But of course we can't see near infrared light, so if we want to display anything with near infrared, we have to shuffle the colours around a bit. And then we get something called a false colour composite. And these are the kind of satellite images you see that have got lots of red in them. Because in this case, what we're displaying as red is actually the near infrared band. So what we're looking at when we see red here is high near infrared values. The green is we're displaying as red, and the blue we're displaying as green. So everything's kind of been shuffled along a bit to fit near infrared in, because we want to be able to see that. And you can see here that the sea is coming up completely black because it's got no near infrared reflectors at all. It's got fairly low reflectors, full stop, but no near infrared reflectors. But also, certain farmers' fields are coming up as distinctly less red than others. Now, those are farmers' fields where nothing is growing. And we can see from space which farmers' fields have things growing or not, even if the crops, when they're growing, look quite like bare earth in the visible band. So things like, certain types of cereal crop, for example, look quite brown when they're fully grown. Which might look like bare earth, but in fact isn't, because we can see this high near infrared reflectors, which shows there's live plants growing there or not. And this is another false colour composite, a shortwave infrared composite. So again, you can start to see differences between the different farmers' fields, which are because of the different reflectances of different types of crops in things like the shortwave infrared and the near infrared. If you go beyond the near infrared into the far infrared and beyond that, the shortwave infrared and far infrared, you find that these sorts of light are released by hot objects. So the amount of that is in relation to the temperature. And this can be quite useful when looking at things like volcanoes. So this is a true colour image of a volcano. Doesn't look like much is going on, you've just got a smoke plume coming down here, looks fairly peaceful. But if you look at a false colour image with some of the thermal bands here to look at temperature, you see a huge temperature anomaly down this flank of the volcano, almost certainly a lava flow down there, but lava flows, contrary to the pictures, don't always look bright orange, they can often look quite black or brown, so you really couldn't see that in this image, but you can when you start looking in these extra bands. So, let's have a little think about why vegetation particularly reflects differently in different wavelengths. This is a diagram of a leaf. You've got the top of the leaf here and the bottom here. Now, I'm not a biologist, but I know a little bit, enough about this, I hope, to explain a bit about how the light interacts with it. So if you have blue light comes to the plant, it goes through the outer waxy layer of the leaf and gets absorbed by the chloroplasts and chlorophyll in the chloroplasts here and turned into energy for the plant to use. Green light, however, hits the outside of the leaf and reflects back again. So it doesn't really do anything in the plant, it just reflects back, and that's why the leaf looks green. Red light does basically the same as blue, it gets absorbed by those chlorophyll molecules and turned into energy. But the near-infrared light goes right down inside the plant and goes to this sort of spongy layer in the middle of the plant where you've got kind of air gaps around the cells. And it basically bounces off these spongy bits and then reflects back very, very strongly through the plants. And that's how you get this overall pattern of high green, or low blue, high green, low red, and then this sudden big jump into high near-infrared reflectors. But the amazing thing is you can also use it to look at how healthy a plant is. Because we all know, for instance, that if we've got a plant that's starting to die on our windowsill, for instance, it goes brown after a while. Well, as you'd expect, when plants get less healthy, the amount of green decreases because the leaves stop looking so green. Now, you can tell this in quite a lot of detail from satellites without waiting for all the plants to go completely brown and die. You can notice small decreases in the amount of green. The other interesting thing is that the amount of near-infrared also decreases as you lose water and nutrients. Those spongy spaces inside the leaf kind of close up, and you don't get this really strong near-infrared reflectance in quite the same way. So you have a reduction in the near-infrared, and you also have this thing called a blue shift of the red edge, which basically means the red edge is this sharp spike here going up to the near-infrared, and that sharp spike moves a bit more in this direction. So we can come up with some fairly simple methods to look at this from satellites and see what's going on. And one of the most widely used methods is something called the Normalized Difference Vegetation Index, or NDVI. And it's a really simple mathematical formula. You just take the value for a particular pixel in the near-infrared, subtract the red value, and then divide by the near-infrared plus the red value. Very, very simple. It's just a simple way of doing a mathematical comparison between red and near-infrared. And you get an output that looks a bit like this. So this is a NDVI image for this area. You can see, first of all, that the water is really low in NDVI values. That's the red values here, really, really low. That's because water has basically no near-infrared reflectance at all. And you can see that urban areas as well have quite low NDVI values. But farmers' fields have a range of NDVI values around here. You know, they're higher in the green kind of area, but some of them are a bit lower. You can easily see bits of vegetation in the middle of cities. So you've got, this is the common here, this whole sort of yellowy area that's a bit higher in NDVI, and there's some bits of the common that are coming up really, really high here. And if you zoom in to a certain area, these are some farmers' fields out to the east of Winchester, you can see obviously there's nothing growing in this field. We know that because there's no near-infrared reflectors, so there's nothing there. It must have been left bare by the farmer. And these sort of methods are actually used by the government agencies that pay farmers subsidies for their fields. So some farmers will get paid a subsidy for leaving one of their fields bare that year. And some of these, a sample of these, are actually checked using satellite imagery and this near-infrared reflectance in the NDVI to see whether they are actually doing what they said they were going to do or not. But more interesting is this field, which has obviously got stuff growing in it, apart from in this area in the middle, so maybe that's a pylon in the middle of the field, or it might be a feeding trough or something. And then there's this area in the middle that's not growing as well as the rest of it. It's not, the plants there aren't as healthy. And that can be quite useful information for the farmer to know. And this is used operationally by farmers in many countries around the world, to a certain extent in the UK, but particularly in countries where they're really limited in the amount of water they can use. So they know exactly where the plants are struggling and where they should put extra irrigation onto their plants. This is a bit more, a slightly more detailed view of a different field. This was taken from a drone, I think, flying over the field. If you look at it in true colour here, you can see, well, you know, there's a few bits, there's some brown bits here where there's not much growing, but the rest of it looks kind of okay. If you look at it in false colour, that's that bit where you're showing the near infrared as red again, you can see there's some areas in the middle of each bit of field that really don't look like they've got as much near infrared reflectance, they probably aren't as growing as well, aren't as happy. But if you look at the NDVI, you can really see it, that there's quite a lot of this field that has got fairly serious issues with growth, and potentially that's to do with where the farmers' tractor wheels are going and killing plants or whatever, but it's something that the farmer might be quite interested to know. The other thing I mentioned here is this blue shift of the red edge, so this line here moving to the left. Well, some satellites have special bands that are located just around here, like 3 or 4 special bands, just for measuring where this red edge is. And that allows you to do some quite interesting things by relating that to the amount of chlorophyll in the plants. Because this position of this red edge is strongly related to the chlorophyll content, because chlorophyll content is one of the things that decreases if the plant gets unhappy for whatever reason. And so you can actually produce some interesting plots like this. So this is a time series of satellite data across the UK. The data's at the top here, I don't really worry about that. This is the beginning of the year, and we're going into summer, and then we're coming back out into autumn and back out into winter, and then looping around again. And this is showing the amount of chlorophyll. Now, of course, you can only see chlorophyll from satellites when plants have actually got their leaves out. When the trees have lost their leaves in the winter, you can't see any of the chlorophyll at all, of course. And this allows you to see the pattern of the seasonality of this greening up of the vegetation, the gaining of the leaves and the losing of the leaves again. So if I just take 3 snapshots from here, you can see that to begin with, we start getting the greening up of vegetation in the southwest here. It then spreads up the country, gets even more intense and spreads all the way up to Scotland. And this is the pattern of springtime happening gradually.
Excuse me, have you got dates for those 4?
Yes.
Here.
Yeah, so this is, let me just look at the screen here. So the top left is March, then early March, late March, early April, late April.
Okay.
So the other thing you can do with this is start to put some numbers on things that a lot of gardeners have noticed about things coming out into bloom or into leaf or into bloom earlier than they would expect. By plotting when you first see this chlorophyll rise at a sort of over time. So here we've got data from the year 2000. This is the day of the year that you saw this green up, they call it, when you start getting these leaves. And you can see that over time, there's quite a lot of noise in it, but over time there's definitely a trend towards green up happening earlier, maybe 5 or 6 days earlier across that decade as a result of climate change. And that's putting numbers on something that a lot of people have observed. Now I said this talk was going to be about monitoring the environment from space, but I'm actually going to stick in a few things about aerial imagery here. And this is a plane that was run until last year, unfortunately it's been stopped now, or it's changed now anyway, by the Natural Environment Research Council to take scientific measurements from the sky. And now everyone thinks when they look at it that these are the cameras. They aren't actually, those are the wheels. Yes. When the other camera comes up after it takes off. The cameras are actually in here, and they've got some very advanced cameras that take similar sort of measurements to satellites, but with one key difference. With a satellite, you might have these 7 different bands. With an aerial imaging system, you get lots and lots of bands across the whole spectrum. So rather than having 7 bands, you might have 700 or 2,000 bands. So you can see things in a huge amount more detail. So rather than seeing these sort of graphs that we saw before, with 7 or 8 points on them, we see these sort of graphs with thousands of points on them. So this is the reflectance of different types of rock. You can see the colours up here, they're basalt, slate, granite, and so on. And you can see that they've all got different patterns to them. There's a big dip here that there isn't in any of the other ones. There's some big dips up there for that one. There's a big dip here, there's a certain pattern here. They all look a bit different. So we can start to classify them again, just like we did with working out where is grass and forest and urban and water. We can work out where's basalt and slate and granite and so on. This is really useful. Oh, sorry, yes, we've got, just to put some context to this graph extends a bit more to the right. So the visible light is down here, this is the infrared, and this is what we call far infrared. So we're looking over a longer range here. And this is quite useful for things like geological prospecting. So if you've got an area of lots of bare ground, like the middle of Australia in the desert, you might want to know where is a good place to try and dig for copper or iron or diamonds or gold or whatever. Now, if you're a geologist, you know what sort of rocks you tend to find, where you're going to find gold, and you want to map those. But sending someone out into the middle of the Australian outback isn't really a very fun thing to do, and it's quite expensive. So fly a plane over it and produce a map like this. This is showing different rock types in a landscape in the middle of Australia. And you can see here these are sort of different patterns that you get for different types of rock that you can distinguish with these computer classification methods. Another interesting application of this was in New York following the September the 11th terrorist attacks. As you know, the Twin Towers both fell down, and they distributed a huge amount of dust all over Manhattan. And that dust was actually quite hazardous. People, particularly firefighters and other first responders, have been dying quite regularly since 9/11 because of the dust they inhaled. There's lots of asbestos and things like that. And you can map this from an aircraft. So they flew an aircraft over just after, this was September the 16th, they flew over, and they've mapped different types of concrete dust and cement dust and so on, and you can see how it's gone up and down the different roads in the road network of Manhattan. Now, so far we've talked mostly about colour and identifying things from colour, albeit colour that we can't necessarily see when we start talking about infrared. But as you said earlier when I asked you about the castle, you can work in black and white as well. You can look at other things like shape and texture and context. And we can apply those things in satellite imaging analysis by using what's called object-based image analysis. So if you look at a map like this, and say we want to classify it into what's roads and houses and gardens and so on. If we zoom in so we can see the individual pixels, we have quite a few difficult decisions to make. Because we've got this kind of edge here of the house. Now, do we classify this pixel here as house or garden? Do we classify that as shed or trees? There's quite a lot of kind of difficulties because things are mixed together. So what you can do is you can start looking at sharp lines. So someone, I can't remember who shouted out sharp lines when I asked earlier how you determine what things were. And you can tell a computer, look at the sharp lines in this image and split it up into lots of objects. So you might go, okay, there's one object, there's another object, there's another one, there's another object. And if you do this automatically on a whole image, you get something a bit like this. So this is a false colour composite. You can see from all the red in the gardens here, and you can see individual buildings have been outlined, bits of gardens, bits of roads have all been outlined automatically by the computer. You can also do it at different levels of detail. So if you do a finer grain segmentation here, you can see actually you've got individual halves of the roof. If you've got a roof like this, you can see both halves of it. And then what you do is you take this sort of image and look at each segment in turn and classify that rather than classifying each individual pixel. So if you've got an individual pixel you're classifying, the only information you have about it is what values it has in the different bands, how bright the light was in the red, the green, the blue, the near infrared, and so on. But if you look at the object, you've got a lot more information. You've got information about the minimum, maximum, and average values for each band. But you've also got things like the shape of the object. Buildings often, not always, but often are kind of rectangular. They have a lot of right angles in them. You can look at neighbours. You can say, well, if this looks like if this has got high near infrared, so it's probably vegetation, and it's surrounded by buildings, then it's probably a back garden. You can look at texture. So, for example, it can be quite difficult sometimes to tell the difference between different types of crops or between forests and grassland. But the texture of a farmer's field and the texture of a forest are very, very different. And if you look across an image, you can see the kind of difference in texture and use that to help you make your decisions. This is also quite useful when the segments change because of an event. So this is after an earthquake. So you've got on the left here pre-earthquake. This is after earthquake here. Not only can you see sort of rubble and things, but you can see that your nice sharp outlines of building segments here are going to look quite different after the earthquake when there's lots of rubble around and lots of buildings have fallen down. And this sort of object-based image analysis is used a lot after things like earthquakes and hurricanes and equivalents of natural disasters to produce maps like this to go out to first responders on the ground saying where is most damaged. And in fact, there's a lovely organisation called the International Committee on Space and Major Disasters, who provide free analysts, and they get free data from all the space agencies. Every satellite operator is signed up to this scheme to do analyses like this very quickly after disasters and send them out to people like Oxfam and Médecins Sans Frontières and the Red Cross and those sort of people on the ground, so they know where the biggest amounts of damage are and where they should focus their resources. Now to switch to another application of satellite imaging, this is a photograph of part of Beijing in normal times, but this is what it was like in January 2013, when there was a really bad air pollution episode there. Now, there's been lots of bad air pollution episodes since then. In fact, a huge amount of the time, the air pollution is very bad in large cities in the east of China. You also have heard in the news recently about poor air pollution in Australia because of smoke from the large bushfires that have been going on there for a while. This particular type of air pollution that you can see in those pictures is particulate matter air pollution, which is lots of tiny little particles in the air that you can breathe in, get deep down inside your lungs and cause huge health problems. And these particles are absolutely tiny. This is a human hair for scale, and PM10, which is one of the types of air pollution, is particles that are less than 10 micrometers in diameter, and they're these blue bits, so they're still fractions of a human hair, and PM2.5, which is one of the more deadly types of air pollution, are these tiny little pink dots on these blue circles. So they're absolutely tiny, and they kill lots and lots of people. So it'd be great if we could monitor those from satellites, rather than having to put lots of air pollution monitoring stations on the ground. And the good thing is we can, but we need to understand a little bit about what happens to light when it goes through the atmosphere. So, the first thing that happens to light when it goes through the atmosphere is that some of the light coming from the sun will hit molecules of the gases that make up the atmosphere. So things like oxygen and nitrogen and carbon dioxide. And some of this light will then get scattered. So it will hit this molecule and it will bounce off, and some of it will bounce back up to where the satellite is. It will come down from the sun and it will bounce back up again. And this happens in what we call a wavelength-dependent manner. So you get a lot more scattering for blue light than you do for green, and a lot more scattering for green light than you do for red. Now this, in fact, is why the sky is blue, because of all the scattering of blue light scatters it around the sun. The scattering is scattered back towards our eyes, and that's why we see the sky as blue. The other thing that goes on is what's called Meade scattering, which is very similar. The equations are different, but this is for bigger particles, so bigger than individual molecules like oxygen and nitrogen, but particles of dust or smoke in the atmosphere. And when the light hits it, again, it's a wavelength-dependent scattering. You get more blue scattered than you get green, and more green than you get red. And again, we can plot these on a graph and start to visualise these. So this is what Landsat would see of a vegetation spectrum if there were no atmospheric effects at all. If there was no atmosphere between Landsat up 700 kilometres in the sky and us on the ground. And you can see what we've seen before: low blue, high green, low red, and really high near infrared dropping off again. But if you put the atmosphere in the way, what you actually get is that. So you can see you get a lot more blue and quite a lot more green than you were expecting, because those are both scattered quite a lot, back up to where the satellite is taking measurements. But actually the rest of it looks pretty much the same, because atmospheric scattering doesn't really affect near-infrared wavelengths. If you then put some aerosols in this atmosphere, so things like dust or smoke that are suspended in the atmosphere, you can see you get even more blue and green. And then you put even more aerosols, a medium amount of aerosols, and this is a high amount of aerosols. And you can see under a high aerosol atmosphere, the value you're recording for the blue has almost tripled, just because of the atmosphere. Now, this is really annoying when you're trying to look at the ground, because you want to see what the true blue and green values of the plants or the urban area were, and you have to try and correct for this atmosphere and get rid of all of these effects. But it's also really handy if you want to work out what's going on in the atmosphere, because then you're trying to do the opposite. You're not trying to correct and remove these effects, you're trying to amplify them and look at them. And just to give a sort of idea, this is the kind of stuff you would see from a satellite. This is a simulated image that I actually created as part of my PhD work. This is London here, Kent and East Anglia. You can see these bits that look like clouds over the image. It's a bit difficult to see with the colours here, but they're actually a bit bluer than you would expect for clouds. and they are the excess blue produced by simulated high amounts of aerosols over those areas. So what we need to do, basically, is look at a satellite image and say, is there more blue here than there should be? And we have various complicated methods for working out how much we think there maybe should be. If there's more blue here than we should be, that's probably caused by aerosols. Let's try and quantify with some models how much that extra bit is and what that equates to in terms of aerosols. And that can produce maps like this. So this is a map of satellite-derived PM2.5 concentrations across the world. So this is the really dangerous type of air pollution. And you can see you get a lot of particles in the air, a lot of PM2.5 in places that are deserts. That kind of makes sense because you've got lots of sand being blown around. You also get huge amounts. You can see the really dark red here on places like the east coast of China, where you've got really bad air pollution, the north of India there. And if you look at Europe in more detail, you see quite high concentrations here. This is the Po Valley in Italy, where there's quite a lot of industry and all of the air pollution collects there because it can't get over the Alps to the north of them, so it kind of sits there. So it's one of the more polluted places in Europe is the Po Valley. And also you can see again in bits of Germany here and in the southeast of the UK, the difference between air pollution values in England down here compared to Scotland and Northern Ireland over here. Of course, you can also do this over time again, like I said about all the previous data. So this is air pollution over time. This is actually a measure called aerosol optical depth, which is slightly different to PM2.5, but measures a very similar thing. And you can see seasonal patterns here. So if you keep an eye on South America, you'll see every so often you get a lot of pollution, and then it goes away again, and then you get a lot more pollution. This is burning of the forest in South America, which only happens in certain seasons, but produces an awful lot of pollution. You can see, again, the amount of pollution changes in the, pollution, the sand in the atmosphere changes over deserts, over time, about what weather conditions are, but generally you've got quite a lot of pollution in places like eastern China here most of the time. So the other thing you can do, the other thing that happens when light goes through the atmosphere, as well as some of it being scattered, some of it is absorbed by things. So again, I actually slightly lied in my previous graph when I showed you things about aerosols because I was actually ignoring absorption. I'll have a quick look at absorption now. This is a similar vegetation spectrum, so you've got the high green and the high near infrared here. And this is with no atmospheric effects at all. But as soon as you put it through the atmosphere, you get this. You get the higher blue and green, as I've already mentioned, due to aerosols and rain scattering. But you get this huge dip here at about 740 nanometers. 760, sorry. And that is absorption by oxygen. So when light hits oxygen, light at about 760 nanometers gets absorbed very strongly by oxygen. So you have a lot of that light missing in your data. And this is actually a really useful way to calibrate data. Because if you're not quite sure whether your wavelengths are being measured in the right place, you look at where this big dip of oxygen is, because of course everything's happening in an oxygen atmosphere, and you can kind of make sure that everything's lined up correctly. But more interestingly, other gases have absorption patterns as well. So if we then put water vapour into our atmosphere, maybe a low concentration of water vapour, you can see the difference. We get absorption features here. So this is about 940 nanometers, and you get quite a lot of absorption there from water vapour. If we increase the amount of water vapour, you see we get even more absorption here. If we increase it again, we get even more absorption. So if we compare the light here to the light just outside here, you can get an idea as to how much water vapour there is in the atmosphere. Now, that's quite useful for people like meteorologists who want to know about the distribution of water vapour in the atmosphere. It's also quite useful from an air pollution point of view because a similar thing applies to lots of other gases, like NO2, nitrogen dioxide, which is an air pollutant that is actually very high in Southampton, for instance, and is linked with lots of health issues. The reason I haven't demonstrated this graph with nitrogen dioxide is because this red line is what the absorption spectrum of nitrogen dioxide looks like. It's quite complicated and nowhere near simple to look at as water vapour, but they use the same approach, but they have to do a bit more work to get maps that look a bit like this. So this is NO2 concentrations across Europe from a nice new satellite that was launched a couple of years ago, producing really great data. You can see the Po Valley again down here, just below the Alps. You can see pollution kind of gathering in the low countries, which it often does. You can see London and its outsides effect here, and the south UK, and again up to, this is kind of Manchester and Liverpool up here, Birmingham kind of down here, and again, very low in the Highlands, but a few peaks for people like places like Edinburgh and Glasgow up there. And if you zoom in a bit more, this is a map from the precursor satellite to that one, in fact, over Southampton, where you can see a spike around Fawley Oil Refinery, which makes sense again, and also the peak areas mostly following the route of the M27, which again makes sense. So, I'm coming towards the end of the presentation now, and once I've had my drink, I just wanted to run through a few other things you can do with satellites, so a very broad selection of other things you can do, just to give you a bit of an idea of the possibilities. This has really just been scratching the surface as to what you can do with satellite imaging these days. So the one other thing you can do with satellite imaging is get the elevation of things, whether that's land or water. They're done slightly differently, but similar sort of approaches are used. So this is a digital elevation model at 30-metre resolution, and this is provided for the whole globe. So you don't have to send someone out with a theodolite and a compass into the middle of the rainforest to work out how high it is. You can look at it from space. This is the local area here. You can see lots of interesting things. You can see Southampton Water. You can see the ridge that goes across the middle of the Isle of Wight, including the Needles here, and that then disappears under the sea before coming out in Swanage with Old Harry's wife, the rocks there. You can see all of the river valleys and the little tributaries coming in from the side. A lot of detail. This is really useful for things like planning purposes, for things looking at what you can see from where. Will there be a hill in the way stopping you seeing the power station or not? It's really useful for flood planning. So if there's going to be a sea level rise of 30 centimetres, how much of Southampton would flood? All sorts of things like that you can see from this. And there's multiple ways of producing these sort of elevation models, but one way is with stereoscopic imaging. So I'm asking you to indulge me a little bit and do a little experiment here. If you hold your finger out in front of you and close one eye, you can either try blinking or put your hand over one eye, and then close the other eye and switch between them, which is a bit difficult to do while talking, you'll see that it looks like your finger is moving. That's because you've got two separate things looking at your finger, and they're in quite very slightly separate places. So they're looking from here and they're looking from there. If, however, your finger is close to your eyes, you'll also get a bit of double vision, but you will also see that it looks like it's moved more when you switch between the two eyes. Because it's closer to you, the offset looks bigger. And that's exactly what satellites do. You have two satellites that are separated a bit on their orbit, like your two eyes that are separated a bit on your face. And they look at the same place from two different angles. And if they see that things look like they've moved a lot between those two angles, then it suggests that the things are close to them, which means they're high places because they're closer to the satellite. If it looks like they haven't moved much, it's because they're far away from the satellite and it's therefore low land. And you can do really detailed elevation models from this stereoscopic imaging approach. The other way you can do, or one of the other ways you can do elevation is by something called LiDAR, which is basically the same as radar, but using light. So radar sends out a pulse of radio waves, which hits something and reflects back, and they time how long it takes, and with things like the speed of light and so on, you can work out how far away it is. LiDAR does exactly the same thing, but it does it with a laser, so it just shines a laser down to the ground, it bounces back up again, and you can do all sorts of complicated things to make it more accurate, but then you can get really accurate elevation models. So this is an area that I did a bit of work on. This is Ulsford in Hampshire, just east of Winchester. It's where the end of the Midhants Railway is, if you've ever been to that. And you can see all the houses, you can see the rise and fall of the land and the roads. You can zoom in detail and see people's houses, trees in their back gardens, bushes, all sorts of things. This is the end of the Midhants Railway with some coaches on the siding here. You can see the trees down the side of the road. You can see huge amounts of detail. And this is really useful, particularly for planning purposes, getting an idea of what's there already and what we change with planning. They're doing a lot of stuff now looking at 5G networks and where to put masts for 5G mobile phone networks, which they're also using this sort of thing for. I mentioned once before that you can look at the heat coming out of things based on their far infrared light. It's a sort of light that comes out when things are really hot. This is a map of sea surface temperature in the Caribbean. So this is Florida down here and the Caribbean islands around here. This is really useful for climate change analysis, obviously, but also for predicting the path of hurricanes, because hurricanes are fed by warm water in the sea. It's the energy that drives them comes from the heat in the ocean, and that can be mapped with this, and you can get an idea, okay, if the hurricane's blowing in this direction, this is how much heat there is, this is what's likely to happen to the strength of the hurricane. All the images I've shown so far have been taken during the day, because the sun's out and you can actually see what's going on. But if you take photos at night, you can see the lights that humans have put in place, the things that come from street lights and lights in buildings and car headlights. Just like in the Second World War, you had the blackout to try and stop German pilots being able to see where cities and towns were. We've got exactly the same thing these days, but it can actually be used for humanitarian purposes. So this is after Hurricane Maria, which hit Puerto Rico a few years ago. This is before, and you can see lots of lights in the main settlement up here in San Juan, and lights in various other settlements. After the hurricane, you can see significantly less lights there and pretty much nothing around the rest of the island, which shows how much damage there's been. And again, it gives you an idea as to the damage experienced in different places. If they're without electricity, that suggests a certain level of damage, and you can use that to, again, try and plan aid after a disaster. So, that's it for the moment. I want to just briefly summarise what we talked about. We started off looking at a castle, just a normal digital photo of a castle, and talked about spectra that you can see there, the spectrum of the castle compared to the sky and the grass and so on, and why that is, why green trees look green. We looked at the spectra, we looked at some satellite imagery, and then looked at how we can look at these spectra in satellite imagery as well, for things like forest and grass and water and so on. We talked about how that can be used for land cover mapping, or how you can look at vegetation in a bit more detail, how you can look at segments and split things up into segments to make it easier to process them, and then we looked at a few other applications like air pollution and elevation and so on. So, thank you very much, and I'm happy to take as many questions as you've got.
Military point of view,
Yeah.
these drones, these, what the Americans can do with these
Yes.
assassinations or whatever, they seem to be very accurate. Is that guided by satellite or?
So they're normally guided basically by GPS. GPS, which is not to do with satellite imaging, but is done by satellites. It's just satellites in space that send out a radio signal. GPS was originally developed by the American military for use for targeting missiles and things like that, and it was opened up then at a lower resolution to the public. So when you get something that's accurate to 10 or 20 meters, if you're a military user and you have a special code that you send off to in your receiver and send off to the satellite, you can actually get sub-millimeter precision sometimes from GPS. And in fact, amusingly, I had to deal with one of these things in a previous job when I was using GPS on something. Civilian GPS receivers are required to automatically turn off if they detect that they're above a certain altitude or going above a certain speed, which basically means they're being used on a missile or a military aircraft or something, and they're required to turn off in that situation, so they can't be used by other militaries, and you know, basically America holds the key to the military use of GPS. What I thought you were going to ask when you started mentioning military is the first question that I normally get when I do a talk like this, which is, if you can see this with commercial satellite imagery, what the hell can the military say? Yeah. And the answer is I don't know, because they don't want to tell me any more than they want to tell you. But it's said that during the Cold War, Ronald Reagan was shown that if he was sitting in the White House garden reading a newspaper, the satellite could tell him which page of the newspaper he was reading. Yeah. Supposedly. And that was the Cold War, that was quite a long time ago, so I imagine they can do huge levels of detail now. But it's pretty amazing that commercial satellites can do under a meter resolution imagery. You can get huge amounts of detail from that.
Can you then see through the clouds?
Right, so you can see through the clouds if you're using radar satellites. So I haven't talked about radar satellites at all here, it's not actually my specialist area. But basically all of the stuff I've shown you is what we call optical satellite imaging. So light comes from the sun, hits the ground and is reflected then and absorbed by the atmosphere and so on, and comes back up to the satellite. So you've got the kind of sun-ground satellite path. Radar uses radio waves that are sent out by the satellite itself. So they ignore the sun entirely and send out radio waves, which are a form of light wave, just further into the spectrum, down, which bounce off the ground and interact with the ground in various different ways and reflect back up again. Now they're affected by clouds a lot less, but they are affected by water vapour. So you do still have to do some sort of corrections for water vapour, but you can basically see through clouds. And you can also do imaging at night because you're not relying on the sun, you're sending out your own illumination in the form of radio waves. And you can do some quite interesting stuff with radar with things like vegetation again, looking at water content in vegetation and the way that light is polarised by certain different surfaces. You often send out waves that are polarised in particular directions and look at what changes to the polarisation. And that allows you to determine a bit more about the ground surface. But it's generally considered a bit more tricky than optical satellite imaging, and the sensors the satellites have to be far bigger and far more powerful because they're sending out their own energy to do it. They're not relying on this big sun that's very conveniently up in the sky for us for optical work. Yeah.
So, sort of related to that, I'm aware that with satellite altimetry, the radar system for monitoring sea levels and that, but one of the ways they calibrate the system is to have active transponders when they know the satellite's going to go over.
Yes.
Is there something similar to that in the optical way of things? I'm thinking of big panels, there's very, very specific colours that they precisely lay down in a certain angle, which when the satellite's coming over. That sort of thing.
So calibration is a big thing for satellites, and obviously you can imagine that if you want to calibrate a sensor that measures light in various wavelengths, you could do that by taking it to something like the National Physical Laboratory and plugging it into all sorts of calibration equipment. But then what you're going to do is you're going to strap it on a rocket and send it up into space. Now with the best will in the world, that's going to knock it around a bit, and it's probably not going to be as well calibrated once it gets up there. And it will sit there getting really hot and really cold and getting hit by bits of space debris and will gradually get even worse. So you need to calibrate it regularly. And in fact, this was some of the work I used to do at the university with my former PhD supervisor, was working on calibration of imagery. And there's various ways of doing it. One of the simplest ways is to use calibration sites on the ground, but for medium resolution sensors like Landsat, we don't build our own calibration sites, like put a big black calibration target out, because it would have to be quite big, and people don't necessarily want us to build those all over the place. So we take places in the world that are really constant in terms of their colour, measure them on the ground with handheld sensors that are the same as the satellite sensors, and then compare them that way. So places like parts of Antarctica, where there are parts of Antarctica that don't get very regular snow, so the surface stays very, very constant year-round over the years. If you measure that maybe once a year, you can use that to calibrate your satellite sensor because you know what it should be measuring. Another place that's been used is salt lakes. So Tuzgulu is a salt lake in Turkey, which a colleague of mine went out and did lots of complicated measurements on to compare to Landsat measurements and to calibrate it over time to make sure the spacecraft sensors weren't drifting away from true calibration. So yeah, there's that kind of stuff you can do. And if you're using planes and things, you often do just put a bit of black tarpaulin on the ground, and you know what the reflectance of your black tarpaulin is, so you can compare it.
So when you've got images from the archives from the 1970s, that was part of that process?
Yes, so theoretically, your images in the archives from the 1970s should be comparable to modern images if you apply the right calibration coefficients to all of the data. Now, I wouldn't want to bet too much on it being perfectly comparable to the 1970s, but definitely from kind of mid-80s onwards, when calibration improved, you've got a pretty good traceable calibration going back there, because that's the other benefit of having multiple satellites in orbit at once. They can compare against each other. So if you've got Landsat 5 and Landsat 7 both flying over, one can fly over 10 minutes later, and then they should be giving basically the same results. And if they're not, you need to investigate why and fix it. Yeah.
So Google Earth, I mean, is that satellite or is that?
So Google Earth is a mixture of all sorts of things. It's more satellite now than it used to be. Basically, it's a mixture of so when you zoom in really close on Google Earth, you zoom in to look at your house. That's aerial imagery. So that's not collected with the really fancy sensors that I was talking about for aerial images that give you lots and lots and lots of data across the whole wavelength. These are basically just big digital cameras that are carried on planes. And they're taking, Ordnance Survey have a couple of planes that they fly around taking these images. A company called Get Mapping do similar things across the UK, and all sorts of companies do it around the world. As you gradually zoom out on Google Earth, it switches from aerial imagery to satellite imagery. And it varies as to where it does that switch, depending on what data is available from that place. And as over time we've got more detailed satellite images available, now you've got satellite images that can go down to a metre, then actually maybe you can use that for some of the really detailed bits, and they will do, but a lot of it's a cost trade-off, because Landsat images and Sentinel-2 images and MODIS images and various things like that are all available for free to anyone who wants them, commercial or not. They're all available for free. They used to cost money. You used to pay about £1,000 for a Landsat image, but in about 2000 or early 2000s, almost 2003 or something, they got rid of all the costs for them. But the high resolution imagery costs, and it costs quite a lot, so you can pay multiple £1,000s for a 1 metre resolution image that covers Southampton. Well, not even the whole of Southampton necessarily. So you can imagine that's quite expensive to cover a whole country at 1 metre resolution. Yeah.
What about the data storage? I'm just trying to imagine how many terabytes per hour are coming from all these systems.
Even just for someone like me who did work on Landsat imagery during his PhD, and I worked on hundreds of different Landsat images from around the world, I have a stack of external hard drives at home. I think I calculated a while back that in my house altogether I have about 20 terabytes of storage, which is significantly more than most people need, because I had lots of satellite images stored. I mean, a Landsat, it varies. So obviously the higher resolution the image, the more space it takes up, and the more bands you have, the more space it takes up. A Landsat image, a Landsat 8 image is probably about 4 gigabytes, which doesn't sound like a huge amount, but you multiply it by 1,000 images taken a day, and that's a lot. So basically, they just have enormous data centres that store these things.
But the whole lot is stored.
The whole lot is stored. Some of the archive Landsat stuff from the 70s, 80s and early 90s is stored on tape with big tape robots that will go through the tape archives and grab a tape and put it in the machine and get the data. So it's still automatic to get the data, it just takes a bit of time. So if you request a satellite image from the 1985, you'll be told it will be available for you tomorrow morning once the robot has gone and got the tape and put it in the machine. But they do store it all. A lot of it is now available quite easily online. Google have got something called Google Earth Engine, which is a scientific tool for using satellite data, which has access to the full archive, basically, of full archive back to maybe 1990 of Landsat, full archive of Sentinel and MODIS and various other things. And what they're doing these days is they're trying to encourage researchers to take their analysis to the data rather than the data, bring the data to their computer to analyse it. So if you're going to write some code to do some analysis on satellite images, the idea is write your code and upload it to Google servers and do it there, or upload it to there's a UK national server called Jasmine, which is a high performance computer that has access to all the satellite data, and you can put your code there and run it there, rather than spending weeks downloading terabytes and terabytes of data onto your local computer to run it on your desk in your office. It's not always possible, but that's what they're encouraging.
I was just thinking that the ozone hole over Antarctica would have been discovered earlier, but the satellite that was perhaps not principally put up there, but put up there to monitor ozone, had an onboard filter that said, well, the received ozone signature was outside this limit, dump that data.
Yeah.
Is there an equivalent of that?
We don't do anything like...
So stuff going over the ocean and they're not interested in the ocean, they just dump all that.
Yeah, I mean, so there are some satellites that are focused purely on land, and they won't do things over the ocean. The biggest problem is not the storage space on the ground; it's the transmission of it from the satellite to the ground. Because to transmit it at a reasonable speed, the satellite needs to be somewhere near the ground station, and there aren't that many ground stations, and so there's a limit to how much data you can downlink every orbit of the satellite. But some satellites are more, I mean, Landsat now collects pretty much every scene it can do, and they're all stuck in the archive because someone might want them one day. In the early days of Landsat, when they charged $1,000 or $2,000 per image, and because it's a US system run by NASA, they used to only keep a certain amount of data for the rest of the world, but keep all the data for the US. Other satellites are very sort of command-driven from the ground. So there's actually a satellite control room in Surrey, in Guildford, for the company Surrey Satellite Technologies, who build some of these satellites. They've got a lovely network of satellites called the DMC satellites, a disaster monitoring constellation, and they're all completely driven by operators on the ground. So operators will say, we want you to take an image there, and there. Every time you see this, take an image. Every time you go to this place, take an image. But ignore everything else, because they sell their images and they only want to take what people are actually going to pay them for. Any other questions? Yeah?
Minor one. What befell Landsat 6?
What befell Landsat 6? It never got to orbit. So Landsat, as you would expect for a satellite series that's been running since the 70s, I've had various issues. Landsat 6, it didn't exactly explode on liftoff or anything, but it went into an incorrect orbit and couldn't be recovered, which is one of the hazards of launching satellites. Nowadays, interestingly, just as a little bit of trivia, a lot of satellites are launched on old intercontinental ballistic missiles that have had the nuclear warheads taken off with arms reduction treaties, but they can still be launched from silos in Kazakhstan. So a number of satellites recently have been launched from silos in Kazakhstan. It's quite impressive apparently watching them. I know someone who was at one of the launches, they kind of pop out of the silo on compressed air and then the rocket motor launches, lights and it zooms up. But you have such a wide range of satellites. These days you have often swarms of mini satellites. So you can get a satellite that's the same size as your washing machine. So one of the DMC satellites I just mentioned that were controlled from Surrey are all about the size of a washing machine. Definitely no bigger than a fridge freezer. And you can launch 4 or 5 of those at once from one rocket. Whereas something like Landsat or MODIS or ENVISAT or some of these big Sentinel-2 are really big ones that take a big rocket being launched by NASA or the European Space Agency. The other interesting thing with Landsat, if I go back to my map of my slide of timeline of Landsat things, you'll notice that Landsat 5 operated for a huge period of time, from 84 until 2013. It actually got the award for the longest permanently operating satellite of any sort. It was amazing that it still worked, but it was just as well that it still worked because we had a run of bad luck. Landsat 6 never got to orbit, as I said. Landsat 7 launched in 1999, but in 2003 it had a failure of something called the scanline corrector. And it's a bit technical to say exactly what it is, but basically the way that Landsat looks at the Earth is it scans across the image. So it looks from the left-hand side of the image across and picks up data as it goes across. It goes like this, backwards. And they've got a physical, mechanical bit in there that does some of the correction for the fact that the satellite's moving while you're doing that, so you get curves, not straight lines. And that broke, which basically meant that every third line of the image was blank. It's a bit of a problem when you're looking at satellite data, and it makes Landsat 7 data a real pain to use. So there was huge celebration when in 2013 Landsat 8 finally got made and put into orbit, and resolved that problem for us.
I thought it was a general rule for all satellites that when you make one, you make a spare.
No, not for these ones. No, some of them are designed to have 2. So the Sentinel series of satellites, which has been launched by the European Space Agency, that has 2 satellites designed to be launched for each of them. They've got Sentinel 1, 2, 3, 4, 5. And they've got 1A, 1B, 2A, 2B. And the idea is you put 2 satellites out there so you get double the repeat period. So you see it every 5 days rather than every 10 days. But no, they don't always build multiple copies, particularly the earlier satellites when it was so expensive to build satellites anyway. And the sensors that you put on a sensor like Landsat are so accurate and so expensive, and just the filters that go in front of the lenses cost hundreds of thousands and things. I mean, it's mad. So you can't necessarily just build loads and loads to have loads spare, let alone the fact that launching it costs a few million quid. Any other
Yeah,
questions?
I think we've come to an end, haven't we? Yes, thank you.
Yeah.
Thank you.
Great, thank you very much.